Hello guys, welcome back again. My name is Amit and it's good time. So in continuation with our DSA series, as we were talking about mathematics and arrays in the last lecture, so we'll be continuing that topic. And in the last lecture, we covered about divisors and what are prime numbers and how do we check if a number is prime or not, and some divisibility rules, not divisibility rules, but how do you count the divisors of a number and how do you find divisors of a number and how do we do prime factorization. So in continuation with the number theory, that basically the essential maths for DSA as well as competitive programming. So in this lecture, we'll be talking about how to find prime numbers in a range from 1 to n, right? So basically, let's say you are given a range, let's say you're given a number n, and you want to find all the numbers that are prime from 1 to n. How do you find those numbers in a best efficient way? We'll talk about that. So let's start the video. So let's start. So the very first thing to talk about is let's talk about what is the basic way, what is the most naive way to deal with this problem. What is a naive way? So as we know that in the last lecture we discussed that if you want to check if a number is prime or not, you can directly check it within square root of n time, right? Let's say you are given a number n and you want to check if it is prime or not, you can check it in square root n time. So one of the the basic ways that you can run a loop for I equal to 1 up till n, and for each number I you can check if it is prime or not, right? For each number I you can check if I is prime, and if it is prime, if I is prime, and if it is prime, then you can push it in your answer vector or whatever it is, right? Then right. So that is basically the naive way that we can approach this problem. So what is the time complexity of this approach? So basically you will be enumerating all the numbers from 1 to n. So this will take, the outer loop will take what, n time, right? Since the outer loop is running from 1 equal to 1 from 1 to n, and you can also start from 2 because we know that 1 is not a prime number. And then for each I, basically you will take what, you will take around square root of I time, right? Square root of I time. So in a way I can say that this whole loop will take how much time. First of all, when we are calculating if 2 is a prime or not, it will take square root 2 time. Then we are going to calculate if 3 is a prime or not, then it will take square root 3 time. In this way we'll check all the numbers, right? So at any point for any I, it will take square root of I time up till we can go up till what, square root of n time, right? So just to take an upper bound on this whole time complexity, I can say that it is around what, n into sqrtn, right? The time complexity of this approach is basically order n into sqrtn. The outer loop works from I from 1 up to n, and the inner loop is working for square root of time. So in order to take a upper bound for this equation, for this whole summation, I'm saying it as order n to square root of n, right? So now the thing is, will this time complexity work? Will this approach work or not? So assuming that your value of n is what, 10 to the power of 5, then I suppose, let's say 10 to the power of 4. It's 10 to the power of 4, then okay, 10 to the power of 4 into 10 and 10 square, right? It is around 10 to the power of 6. Okay, this will work. This will work because the constraint is up till 10,000, right? Let's say I increase the value. Let's say I increase the value on my constraint is what, 10 to the power of 6. Then it goes to 10 to the power of 6 into 10 to the power of 3, which is around 10 to the power of 9. Will this approach work? This approach will not work, and you will get a TLE. This means that this is not a very efficient way of finding a prime, for finding prime numbers in the range from 1 to n, right? So then what do we do? What do we do? This is not efficient. Here comes the life savior, and that is the Sieve of Eratosthenes. The Sieve of Eratosthenes. So I'll just write it down. We'll be talking about Sieve of Eratosthenes. It is actually a very amazing algorithm. Okay, if you go ahead and read about it on online, you will see what magic this algorithm has. So basically the very core idea of sieve of Eratosthenes is that it marks the multiples of prime numbers. Okay, the very core idea, the very core idea is to mark the multiples of prime numbers. Okay, so what do we do is, so since we talked about when n is 10 to the power of 6, it will the previous algorithm is not going to work. So let's say what do we do is that we create some sort of array. We'll create some sort of an array, okay, and then we'll keep on marking the numbers as prime or not prime. So basically after the complete process is over, all the prime numbers that are present will be marked as true, and all the composite numbers that are basically the multiples of prime numbers will be marked as false. So prime will be marked as true, and composite or non-prime, I'll say non-prime. Why non-prime? Because we are also considering 1 and 0 in this case. So not 0, but basically 1 we are considering. So that's why we are saying non-prime. So these will be marked as false. So then after we are over with this process, all the numbers that are marked true will be our prime numbers, and we can directly get them. Okay, so the core idea is basically to mark the multiples of prime numbers. Why? Because every number that is composite, if you prime factorize it, you will see that each number is actually a multiple of what? Prime numbers only, right? When we multiply a bunch of prime numbers together, let's say it's only a single prime number or multiple prime numbers in some power, we get a numbers, right? So basically the core idea is to mark the multiples of prime numbers. Okay, so then how do we do it? How do we do it? And what is the time complexity of this approach? Let's try to first see how this thing works. Okay, I'll take a shape. Okay, okay. So let's create an array. Let's create an array. I hope this is visible to everyone. Okay, okay. So let's create the array for 25 numbers. So this, let's say, if my counting is correct, 0 and 1, then 2, 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10, then 11, then 12, then 13, then 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25 is this. Let's number them up. Okay, let's number them up. So we have what? We have 0, we have 1, we have 2, we have 3, we have 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15. Just you have to wait with me and it will be over soon. 20, 21, 22, 23, 24, and 25. Okay. So we have now our array, right? So this array is basically called as sieve. Okay. So remember this thing. This whole array is actually named as sieve. Okay. So basically, when we are saying Sieve of Eratosthenes, so Eratosthenes was basically the mathematician who founded this, who found this algorithm, right? Who made this algorithm, and sieve is basically a representation. This whole array that you see is basically called as sieve. So that's why it's called Sieve of Eratosthenes. And let's see how this how this process works. That first of all, what we'll do, we know that 0 and 1 are not prime. So what we'll do, we'll initially what will happen. Let just me here is this one. Fuck. Okay, I think I'll. Okay, 1 minute, 1 minute. Okay, okay, not a problem. So we are back. Okay, so what we initially do is that. Okay, so initially we assume that every number is prime. Okay, initially we assume that every number is what? Every number is prime. So initially every number from 0 to 1 is marked as true. Okay, these all are marked as true, that these numbers are actually prime. That is what we assume at the starting of the algorithm, right? Let me write T. Okay, okay, and we are there. Okay, so initially we assume that each of these numbers from 1 to n, basically we are going to calculate the the prime numbers from range 1 to n, and that's why this algorithm, that is what for this algorithm is used. So basically we assume that every number is prime. So we start off, first of all, we start off by saying that 0 and 1 are basically not prime, right? We know that these two numbers are not prime. So initially we will mark both of them as false. Okay, we mark both of them as false. Then we start from 2. Basically our algorithm starts from 2. So we know that 2 is prime. Okay, we can see that the value at the cell 2 is basically true. So it means that this number is prime. So now what do we do? What do we do is that we start marking the multiples of number 2. So what are the multiples of 2? 2 into 2, 4. So we'll start from 2, not from 2 into 1, because 2 into 1 is basically 2 and 2 itself is a prime. So we'll start from second multiple, right? So let me write it again. Okay, so yeah. So first of all, we have 2 into 2. So this is 4. So since we are going to mark the multiples of 2, so we can see 4 is present. So we'll mark 4 as false. Okay, this is false. Okay, then we go to 2 into 3, which is 6. So we mark 6 as false. Okay, this has been marked as false. Then we go to 2 into 4, which is 8. Then we mark 8 as false. Okay, that this is not a prime because it is a multiple of 2, right? Then we go to 2 into 5, which is 10. So we mark 10 as false. That this is not a prime. Then 2 into 6, we have 12. 12 is not a prime. And then we go to 14, which is not a prime. Then 16, it's not prime. 18 is also not a prime. 20 is also not a prime. 22 is also not a prime, right? And then 24 is not a prime. And finally we are over, right? So we have covered all the multiples of what? We have covered all the multiples of number 2, right? From 1 to n, right? Let me just write it properly. So 2 into 7 is 14, and 2 into 8 is what? 16. Yeah, I think you'll not need more than this. Okay, so in the first go, we have covered all the multiples of number 2. Okay, so now we can see that 2 is our prime number. Okay, let's move on next. We can see the very next number, that is 3, is also true, right? Is also true. We can see that 3 also is currently true. This means that 3 has to be a prime number, because from the previous iteration it hasn't already been marked as false. Remember, if a number is already marked as false in the previous iteration, it means that it is not a prime number. And if a number has survived the previous iterations and has not been marked as false, it will mean that the number is prime, and that is why it's marked true. So we'll start from 3 now. So we'll start marking the multiples of 3. So where do we start? Do we start from 3 into 2? Should we start from 3 into 2? No. Why not? Because see, look at this point. Look at this point. You will see that 2 into 3 has already been covered, right? Is there a need to cover 3 into 2 another time, right? See, when we move forward, we'll also see 5 into 3 and 5 into 2. So we can see 2 into 5 and 3 into 5 would have already been covered. That is 15 would have been covered by 3 itself. So that's why when we use our algorithm, we actually start from I into I. We'll start from 3 into 3. Okay. So what do? We do not start from 3 into 2, but we start from 3 into 3 into 3. Why? Because the previous multiples that are of 3, let's say the other multiples of 3 are what? Well, let's talk about the multiples of 3 which are lesser than which are lesser than 3, like 3 into 1 and 3 into 2. 3 into 1 is not composite. We'll talk about 3 into 2. So 3 into 2, we can see it has already been marked, that is 6. So there is no use of going back again and marking it again, right? In a similar way, when we talking about 5, so we'll start from 5 into 5. We'll not talk about 5 into 2 or 5 into 3. Why? Because 5 into 2 has already been covered here, and 5 into 3 has already been covered in the form of 3 into 5 here, somewhat here, right, as 15. So that's why when we run Sieve algorithm, we always start from I into I, because the previous multiples have already been covered by previous prime numbers, right? That's why. So let me just remove this part and I'll write it again. Okay, so we start from 3 into 3. Okay, so 3 into 3 is what? 3 into 3 is 9. So we mark 9 as false. This is false. Then we go to 3 into what? 4. 12, right? So we can see that it has already been marked. So now one would argue that bhaiya ye bhi to pehle se marked hai, why are you going through this? Okay, see, the thing is that this time the multiple is actually bigger, right? We do not have to care about the multiples which are smaller than 3, right? Like 3 into 2, 3 into 1, we do not have to care about them, right? क्योंकि वो पहले से कवर हो चुके हैं. जो कि बड़े हैं, the bigger multiples have to be taken care of, चाहे उनको दोबारा भी कवर करना पड़ जाए, right? That's why ये 12 दोबारा कवर हुआ. Then we go to what? 3 into 5, which is 15. So we mark 15 as false. Okay. Then we go to what? 3 into 6, which is 18. So 18 is also marked already, so not a problem. Then we go to 3 into 7, which is 21. So 21 has to be marked as false. Then we go to what? 3 into 8, which is 24. And it has already been marked. So again, we are over with the process of 3. So हमने सारे 3 के multiples cover कर लिए, right? All the multiples of 3 have been covered. So now let's move ahead. Now we have covered the multiples of 2. We have covered the multiples of 3. We have got two prime numbers, 2 and 3. Now we move to 4. We can see that 4 has been marked as false. This means that it's not a prime number and we'll not be checking its multiple, right? So we'll just move forward to 5. Now we see that 5 has not been marked as false. This means that 5 is true, right? 5 is true, which means that 5 has to be a prime, right? So what do? We start from 5 into 5. We'll not start from 5 into 2. We'll not start from 5 into 3. We'll start from 5 into 5 and not also from 5 into 4. 5 into 4 से भी नहीं करेंगे because वो पहले से cover हो चुके हैं. Why? Because 5 into 4 is what? 5 into 4 is basically 2 into 10, which is 20, right? So वो already cover हो चुका होगा 2 के multiples में. That's why we'll not cover 5 into 4 again, right? So 5 into 5 is what? 25. So we'll directly jump from what? Here to here, and we'll cut 25 and mark it false. And then we can see 5 into 6 का कोई मतलब नहीं है, and there is no use. So not a problem, right? 5 into 6 का use नहीं है. Then we go to what? 6 has already been marked, so we'll move to 7, and 7 into 7 is what? 49. So we can see that we have already covered all the numbers, because now 7 into 7 जो है वो पहले से क्या है 25 से बड़ा हो चुका है, right? 7 into 7 is what? Greater than 25. It is 49. So this means कि अब हमें आगे चेक करने की जरूरत नहीं है. If anyone has not seen the previous lecture, then you can go ahead and watch the previous lecture again. The link will be in the top right corner, right? So in that video I have told कि you basically only need to check up till square root of n factors to check if what are the factors of a number. Let's say if you want to check the divisors, or if you want to check if a number has factors, then you only need to check up till square root of n time, right? And that is why this loop is basically running up to I into I less than equal to n. That is basically square root of n time. So basically when this becomes 6, we'll not move ahead, right? When this becomes 6, we'll not move ahead, because हमें पता है कि इसके बाद हमें multiples वैसे भी नहीं मिलने वाले, right? क्योंकि factors जो होंगे ना नंबर 25 के, remember इफ द फैक्टर्स ऑफ 25 आर कंस्ट्रेंड विद इन लेस देन 5, ठीक है, कि हम 5 से कम में 25 के सारे फैक्टर्स को निकाल सकते हैं, देन वी कैन फॉर श्योर से कि 24 के जो मल्टीपल्स है ना, वो भी उसी रेंज में हमको सारे मिल जाएंगे, 5 के पहले पहले ही हमको सारे वो मल्टीपल फैक्टर्स मिल जाएंगे. दैट्स व्हाई देयर इज नो नीड टू मूव अहेड फ्रॉम 5 एंड देयर इज नो नीड टू चेक फॉर दीज नंबर्स, राइट. इनके ऊपर आइटरेट करने की जरूरत नहीं है. Why? Because we know that factors of number 25 will always be less than equal to 5, right? उसी के अंदर हमको उसके सारे जितने भी डिवाइजर्स है ना वो मिल जाएंगे, right? जितने भी डिवाइजर्स हमको मिल जाएंगे. Okay, I'm not saying कि factors 5 से बड़े नहीं हो सकते. I am trying to say you'll be able to get all the divisors within less than equal to 5. Okay, so we'll not move forward. Now let's see all the numbers that are left in this array that have not been marked yet, जो कि अभी भी ट्रू हैं. Those are basically the prime numbers from 1 to 25. आओ देखते हैं वो कौन कौन से numbers हैं, right? Let's see. So first number that we have is what? That we have is 2. Okay, so 2 is basically a prime. Very good. Then we have 3, right? 3 has also been marked, has not been marked. Then we go to 5. 5 भी mark नहीं हुआ है, so 5 is also a prime number. Then we go to 7. 7 is also not marked, so we write 7. Then we can say that 8 and 9 has been marked, 10 has also been marked, then 11 has also not been marked, so 11 becomes a next prime number, right? Then 12 has been marked, 13 has not been marked, so 13 is also a possible answer, right? Then we have what? Then we have 14, 15, 16, then we have again 17, and then we have 19, then we have 23, right? So then we have what? 17, 19 and 23. So these are basically the numbers that are prime from 1 to 25. From 1 to 25, right? So was this a good method? Yeah, it was a very good method, right? अच्छा लगा ये? It is actually very, very maths based. If you are interested about mathematics, or you have just simple logic, you'll see कि the beauty of this algorithm is that कि simple maths use कर रहा है, कोई ऐसे बहुत कॉम्प्लेक्स एडवांस मैथमेटिक्स का रिक्वायरमेंट नहीं है, बट इट इज सो एलिगेंट एंड इट इज सो सिंपल, और फिर भी कितना पावरफुल. दैट्स व्हाई वी यूज इट इन अ लॉट ऑफ प्रॉब्लम्स. इट माइट बी पॉसिबल कि आप बहुत सारे क्वेश्चंस में आपको सी यूज करना पड़ेगा whenever we are talking about a prime in a range, or when you are dealing with factors in a number, then where we have to check prime or not, then in most of the cases you will be requiring sieve, क्योंकि sieve से हम लोग प्री प्रोसेसिंग कर लेते हैं लॉट ऑफ क्वेश्चंस. सी अगर आप हर एक नंबर को ना बार बार प्राइम चेक करोगे तो उसमें स्क्वायर रूट टाइम जाता है. सो व्हाट डू वी डू जनरली इज इन क्वेश्चंस वी प्री प्रोसेस ऑल द प्राइम्स फ्रॉम 1 to n पहले से ही. सो दैट विल बेसिकली द लुकिंग ऑफ प्राइम कि ये नंबर प्राइम है कि नहीं, दैट विल बेसिकली चेंज आर चेकिंग अप लुकिंग अप फ्रॉम स्क्वायर रूट ऑफ n टू ऑर्डर 1, क्योंकि हमने पहले से ही प्री प्रोसेस कर लिया है, निकाल लिया है कि व्हाट आर नंबर्स आर प्राइम फ्रॉम 1 to n. ठीक है, this array would be having all the numbers that are prime with marked as true, so we can directly check if the number is prime or not in order 1, right? So pre processing में बहुत काम आता है. Now let's talk about the time complexity of this piece of code. So बहुत लोगों को ये लग सकता है कि भैया you are marking the multiples, right? And at the same time, since we can see that the outer loop is running what? The outer loop is running in this form, right? I into I less than equal to n, right? In this way. तो किसी के दिमाग में आ सकता है कि भैया कुछ स्क्वायर रूट n टाइप का होगा, कुछ n into कुछ स्क्वायर रूट n का फैक्टर आ रहा होगा. No, it is not the square root of n factor. Okay. If you basically see the code, okay, एक बार ऐसा करता हूँ मैं, बेसिकली पहले कोड कर ही देता हूँ इसको. Okay, we'll just go to code part. Just give me a minute. Okay, so let's start coding the approach, and then we'll talk about the time complexity of this approach and the space complexity. Okay, so first of all, we'll take the input of number n. So basically, the number where from 1 to basically n, we'll be calculating the prime numbers. So first of all, what do? We use a boolean. We create a boolean array vector of bool. Okay, and let's say it has called as prime. Okay, primes and n plus 1 comma true. So what are we doing? Initially, we are declaring every number from 1 to n as a prime, right? As I said, what do? We declare every number as prime. Declare every number from 1 to n as prime. Good, nice. Okay, now what do? First of all, as I said, that we'll mark 0 and 1 as non-prime, right? We'll mark them as non-prime, क्योंकि हमें पता है कि वो प्राइम नहीं है, they are basically not going to help our case, right? क्योंकि 1 के मल्टीपल्स को चेक करने का कोई मतलब नहीं, क्योंकि 1 के मल्टीपल 2 भी होता है, 3 भी होता है, 4 भी होता है, 5 भी होता है, तो इसका मतलब के सारे कॉम्पोजिट है? नहीं, ऐसा नहीं है. That's why we'll not be checking for 0 and 1. We'll directly mark them as false, that they are not prime. Okay, now what do? Now we start our process like for int I equal to 2. As I said, that we'll start from 2, and I into I is less than equal to what? Less than equal to n and I plus plus. Okay, now what do? If primes of I, what does if primes of I mean? So basically, if primes of I means that the current ith number is true or not. If the current ith number is true, it means that it has not been marked as false in the previous iteration. इसका मतलब पिछले जितने भी प्राइम नंबर्स निकले हैं और जो करंट नंबर है वो किसी का भी मल्टीपल नहीं है. दिस मीन्स कि भैया ठीक है, ठीक है. रिमेंबर दिस थिंग, सिंपल सी बात है कि एक बड़ा नंबर हमेशा एक छोटे नंबर का मल्टीपल होगा, राइट. 4 कैन बी अ मल्टीपल ऑफ 2 बट 2 कैन नॉट बी अ मल्टीपल ऑफ 4. सिंपल सी बात है, एक बड़ा नंबर हमेशा छोटे नंबर से मल्टीप्लाई करके बनेगा और एक छोटा नंबर बड़े नंबर से मल्टीप्लाई करके नहीं बन सकता है. दैट्स वाई अगर कोई नंबर हैज नॉट बीन मार्क्ड एज फॉल्स इन द प्रीवियस आइटरेशन, जो कि छोटे नंबर्स थे उससे, इट मींस कि अब अगर ये अभी तक मार्क नहीं हुआ है, इसका मतलब इट हैज टू बी प्राइम. क्यों? क्योंकि इसके आगे वाले नंबर जो है उसका ये मल्टीपल कभी हो ही नहीं सकता. 3 कैन नेवर बी अ मल्टीपल ऑफ नंबर 5, right? 3 can never be a multiple of number 5, right? But 3 has a chance of being a multiple of 2, पर वो होता नहीं है. That's a different thing. ठीक है, पर हमेशा जो बड़ा नंबर है वो छोटे नंबर से मल्टीपल होगा, राइट? ऐसा नहीं कि बड़े नंबर का मल्टीपल बन जाए, right? So that's why we check कि current number जो ith number है that is true or not. If it is true, this means that we have landed a prime number, and what we'll do, we'll just move ahead and we'll start marking its multiples. So for int j equal to what? As I said that I will start from I into I always. क्यों? क्योंकि जैसे हमने देखा था कि 5 into 5 का केस कि 3 into 5 और 2 into 5 have already been covered, तो उनको दोबारा चेक करने की जरूरत है नहीं, right? So what do? We start from I into I. Remember, we do not start from 2 into I, we start from I into I. Okay, और वो टाइम बचाने के लिए ही था बेसिकली. Then what do? I less than equal to n and I plus equal to what? Not I, what have written? It's j less than equal to n and j plus equal to y. सिंपल सी बात है कि जो नेक्स्ट मल्टीपल होगा उसमें वो कैसे मिलेगा, वो i प्लस करने से मिलेगा. जैसे तुम्हारा 2 है तो नेक्स्ट मल्टीपल क्या है, 4 है. 4 के बाद नेक्स्ट मल्टीपल क्या होता है, 6 होता है. 4 प्लस 2, देन 6 प्लस 2 8, 8 प्लस 2 10, 10 प्लस 2 12, राइट? इस तरीके से आप बढ़ते हो. सो व्हाट डू वी डू नाउ? वी जस्ट मार्क देम एज फॉल्स and that is all. Mark multiples of I as false. Okay, this means ith number is prime. And actually we are over with the code of Sieve of Eratosthenes. इतना ही 3 लाइन का कोड जो आपको दिख रहा है, this is basically the code of Sieve of Eratosthenes. A very short code, a very small code, but a very powerful tool and a very elegant algorithm. Okay, it's just mind blowing, right? अब इसको जरा यूज करके इसके प्राइम्स प्रिंट कराते हैं. फॉर इंट i equal to 1 not equal to 2, I less than equal to what, n and I plus plus. If primes of I, अगर नंबर प्राइम है, so we'll print it. Okay, cout I and print it, and after it what we'll do, cout slash n. Okay, for getting the next line. Okay, so we are done with the code. Okay, now let's try to run this piece of code. G++ save. A.exe, and let's take a number like 5. What happened? Okay, I don't know what happened. Let me check again. Okay, I have to take the number input. I haven't taken the number as input. Okay, let's try to run this piece of code again. Okay, let's take 5. So we can see we have 2, 3 and 5. 2 and 3 and 5 are basically our prime numbers, right? Now let's take some other input like 1. So we can see nothing has been printed, which means कि कोई भी prime number नहीं है. Let's take 2. We get 2. Now let's take 25, right? जो कि हमने example use किया था. We have what? We have 2, 3, 5, 7, 11, 13, 17, 19 and 23. जो भी हमने ढूंढे थे वही हमको मिल गए. We can see 2, 3, 5, 7, 11, 13, 17, 19 and 23, right? So in this way basically we generate all the prime numbers. एक केस ले लेते हैं, like let's say 14, not 14, एक कोई बड़ा नंबर लेते हैं. Let's take 10,000. So we can see कि इतने सारे प्राइम नंबर्स हैं. And you can actually also take a count. आप काउंट भी रख सकते हो. What we'll do, एक काउंट भी रख लेते हैं. Okay, int c and t equal to 0, and if it is ever a prime we'll just update our count, right? So बाहर आके यहाँ पर पहले लिख देते हैं कि cout all prime numbers, right? और हमारे सारे नंबर प्राइम नंबर्स प्रिंट हो जाएंगे. एंड आफ्टर दिस विल जस्ट प्रिंट cout count of primes would be equal to what, cnt slash n, right? So इसको रन करके देखते हैं दोबारा. We have 25, so we can see 9 primes are right. Let's take 10,000 as we said. So we can see that there are 12,000. We have 1,229 prime numbers between 1 up to 10,000. If you go up to 10 to the power of 6, let's take 10 to the power of 6. We can see it's working. Okay, It's basically printing. Yeah. So we have got our value. So we can see it is around what 78,498 numbers of prime from 1 up to 10 to the power of 6. Right. So in this way, basically, you will use sieve to get all the prime numbers from 1 up to n. But the thing is, ये तो लिख लिया. But why sieve? But why sieve? कि sieve की फायदा sieve को यूज करने का फायदा क्या है अगर हमारा ऑप्टिमाइजेशन नहीं है. Okay. So let's talk about why is this a better approach? Why is this a better approach? So basically, the time complexity of sieve, the time complexity of sieve is order of n into log of n. Okay, remember this. It is not square root of n into square root of n. It's not n into log n. It's n into log of n. ठीक है. n के बाहर 2 बार log है. ठीक है. पहले log n लिया, जो log n आया है उसका भी log ले लो. ठीक है. उसको n से मल्टीप्लाई कर दोगे and that is basically the time complexity of sieve of Eratosthenes. ठीक है. ये टाइम कॉम्प्लेक्सिटी होती है. इसकी स्पेस कॉम्प्लेक्सिटी क्या होती है? इसकी स्पेस कॉम्प्लेक्सिटी होती है एज वी नो कि हम एक एरे क्रिएट कर रहे हैं n साइज का, तो इट इज ऑर्डर n. ओके, सो स्पेस कॉम्प्लेक्सिटी इज ऑर्डर n एंड द टाइम कॉम्प्लेक्सिटी इज n into log of log n, जो कि काफी कॉम्प्लेक्स है. देखने में किसी को भी वो कोड देख के नहीं लगेगा कि इट हैज सम दिस काइंड ऑफ अ कॉम्प्लेक्स टाइम कॉम्प्लेक्सिटी, बट इट इज ट्रू. ओके, इट इज ट्रू. ठीक है. नाउ आई जस्ट ट्राई टू गिव यू एन ओवरव्यू. ठीक है. द एक्चुअल प्रूफ ऑफ दिस टाइम कॉम्प्लेक्सिटी इज वेरी कॉम्प्लेक्स. Okay, if you go about and search about this, the proof of this time complexity, the exact proof, the mathematical proof is actually very complex. ऐसा क्यों होता है? एक बार जरा समझते हैं कि sieve करता क्या है. As I said in my previous, when I was starting the video, I said the core idea of sieve is to mark the multiples of prime numbers, right? To mark the multiples of prime numbers. So basically, the time complexity is what? Whatever time complexity that we take upon marking the multiples of prime is basically equal to the number of iterations. So सबसे पहले 2 के सारे मल्टीपल्स मार्क करने में कितना टाइम जाएगा? n by 2 ना, राइट. फिर 3 के n by 3, फिर 5, फिर n by 7, फिर n by 11. तो जितने भी प्राइम नंबर्स है 1 से लेके n तक, उन सब के आप क्या कर रहे हो? मल्टीपल्स को मार्क कर रहे हो. सो बेसिकली द टाइम कॉम्प्लेक्सिटी ऑफ दिस अप्रोच इज इक्वल टू द समेशन ऑफ दिस सीरीज. समेशन ऑफ दिस सीरीज. सो वी कैन सी n by k. सो यहाँ पर k एक प्राइम नंबर है, राइट. So this summation is basically the time complexity of sieve, right? अब इसका समय जो वैल्यू है ये n into log of log n कैसे आती है, ये आपको समझना पड़ेगा. ठीक है. इसका एग्जैक्ट प्रूफ इज एक्चुअली वेरी कॉम्प्लेक्स. दिस बेसिकली अ प्राइम हार्मोनिक सीरीज. अब हार्मोनिक सीरीज बहुत लोगों को अगर नहीं पता है, सो यू माइट हैव हर्ड अबाउट ज्योमेट्रिक प्रोग्रेशंस, यू माइट हैव हर्ड अबाउट अरिथमेटिक प्रोग्रेशंस. ठीक है. देन राइट, एपी का ही जस्ट उल्टा कर दो. ओके, सो एपी के जो टर्म्स होते हैं ना अरिथमेटिक प्रोग्रेशन के, उन्हीं का इनवर्स ले लोगे तो दैट बिकम्स एचपी, राइट. So this basically what? This basically a harmonic series. It is a prime harmonic series. और इसके कुछ proofs होते हैं, Dirichlet series होती है. People who have some who have taken some advanced mathematics, they might be able to get about the Dirichlet series, and some multiplicative bounded functions. They'll know about it. But for just for you people, I will give the proof, but a very loose proof. ठीक है. I'll not give the complex proof जो कि आपको बिल्कुल समझ ही ना आए. I will not give that proof. But मैं आपको ऐसा proof दूंगा that anyone who has taken basic 12th class maths और बेसिक इंटीग्रेशन, अगर बेसिक आपको समेशन आता है तो यू विल बी एबल टू गेट द होल्ड ऑफ इट कि आखिर बेसिकली क्यों n into log of log n आता है. ठीक है. आई विल नॉट गो इनटू एडवांस एंड ग्रेजुएट लेवल मैथमेटिक्स जो कि बच्चे कॉलेज में जाके पढ़ते हैं, फिर पोस्ट ग्रेजुएशन में पढ़ते हैं. आई नॉट डील विद दैट. बट मैं आपको एक बेसिक तरीका बताऊंगा, एक लूज प्रूफ बताऊंगा दैट विल स्टिल बी एबल टू गेट यू कि n into log of log n कैसे आ रहा है, राइट. So here are some properties of prime numbers. Okay, here are some properties of prime numbers जो कि आपको पता होनी आपको पहले जाननी होगी before starting off with the proof. Okay, we are going to prove the time complexity. Okay, proof. Okay, so first property of prime numbers is there is a theory called prime number theory. Okay, there is something known as prime number theory. Okay, इसको आप चाहे तो जाके पढ़ सकते हो, but that is not actually required. But we only need two postulates from this theory. The first first postulate is the number of primes, the number or count, you can say count of primes from 1 to n is nearby equal to n divided by natural logarithm of n. Okay, remember this thing. This is a very important postulate. कि the count of prime numbers of 1 to n is around n divided by log of n. This log of n is basically the natural logarithm. Okay, ठीक है. कोई डरने वाली बात नहीं है. ओके, और दिस बेसिकली ट्रू फॉर लार्ज नंबर, लार्ज वैल्यूज ऑफ एन। अगर आप एन की लार्ज वैल्यूज को प्लग इन करोगे, द अप्रोक्सीमेशन, दिस बेसिकली एन अप्रोक्सीमेशन पॉइंट, ये एग्जैक्ट नहीं होता है। ओके, रिमेंबर दिस इज नॉट एन एग्जैक्ट वैल्यू, बट दिस इज बेसिकली एन अप्रोक्सीमेशन दैट द काउंट ऑफ प्राइम्स फ्रॉम 1 to n is around n divided by natural logarithm of n, n into ln of n. Okay, and then the second postulate is the kth prime, the kth prime number is of the form, is of the form k into ln of k. ओके, k into ln of k, ये दो चीजें याद रखोगे, बस इतना ही याद रखना। क्या, द काउंट ऑफ प्राइम्स इज अराउंड n into n डिवाइड बाय ln of n, और जो kth प्राइम नंबर होता है वो किस फॉर्मेट का होता है, वो होता है k into ln of k। इसमें वन जो होता है ना, k इक्वल टू वन, एक वो होता है हमारा एक्सेप्शन, क्योंकि k इक्वल टू वन 2 से शुरू होता है। सो बेसिकली द फर्स्ट प्राइम नंबर इज 2, सो 2 में ये प्रॉपर्टी फिट नहीं होती, तो हम उसको अलग से डील करेंगे। बट अगर कोई भी और प्राइम नंबर उठाओगे, तो दैट जनरली फॉलोज दिस फॉर्मूला, कि जो kth प्राइम नंबर होता है दैट इज अराउंड k into ln of k। बट द पॉइंट इज दिस इज नॉट एन एग्जैक्ट वैल्यू। ओके, अगर आपको लगता है कि आप इस फॉर्मूले का यूज करके कोई भी प्राइम नंबर निकाल सकते हो, दैट इज नॉट ट्रू, दैट इज स्ट्रिक्टली नॉट ट्रू। ये फॉर्मूला हल्का सा गलत भी होता है, बट थिंग इज इट कैन गिव यू समवॉट लूज बाउंड, आपको एक आइडिया एस्टिमेट दे सकता है। दैट्स व्हाई वी आर गोइंग टू यूज दिस प्रॉपर्टी। ठीक है, दिस इज नॉट एन एग्जैक्ट थिंग, राइट। ओके, अब हमें दो चीजें मिल चुकी हैं। नाउ वी कैन फॉर्मली स्टार्ट अ प्रूफ, वी कैन फॉर्मली स्टार्ट अ प्रूफ। ओके, सो द फर्स्ट थिंग इज कि हमारा समेशन था क्या। it was what, it was n by 2, then it was n by 3, then it was n by 5, then n by 7, and so on, right, and so on. Let's take it until infinity, but still not a problem, I'll not write infinity because हमारा n bounded होता है। okay, इस तरीके से एक समेशन सीरीज हमारे पास होती है, right? So what I can do, I can actually take out n common, right? I can take out n as common, and we'll be left with 1 by 2 divided by 1 by 3, 1 by 5, and then 1 by 7, and in this way, right? So this basically what, ये तो हमारे पास n बाहर आ गया, right? This n we have got, right? This n we have got, we need to find the summation of this part, right? ये तो हमें मिल गया। Let's talk about the summation of this part. What is this? This is basically the summation of inverse of prime numbers, right? In other words, I can write this whole summation as what? Let's say that this is s of, this is s. Let's say Sn. So what is Sn? Sn is basically a summation of what? From I equal to 1, not I equal to let's say k. Let's say k equal to 1 up till what? n divided by ln of n. As I said कि 1 से लेके n तक कितने प्राइम नंबर्स होते हैं? n divided by ln of n. So we can see कि ये जो सीक्वेंस सीरीज हमारे पास है, इसमें कितने टर्म्स होंगे? इसमें अराउंड n divided by log n times of n, इतने टर्म्स होंगे हमारे पास। ओके, दिस विल बी द काउंट ऑफ टर्म्स, एंड वील बी स्टार्टिंग फ्रॉम k इक्वल टू 1, और हम क्या सम अप कर रहे हैं? वी आर बेसिकली समिंग अप k ln k, राइट? अब देख लो, हमने दोनों पोस्टलेट का यूज कर लिया, द काउंट ऑफ प्राइम्स, और जो आई प्राइम, जो केयर प्राइम नंबर होता है, वो किस फॉर्म का होता है। सो दिस बेसिकली वी कैन लूजली राइट दिस होल समेशन in the form of this summation, right? We can loosely write this complete summation in this form, right? अब इसको जरा एक्सपैंड करते हैं। इसको एक्सपैंड क्या करते हैं, इसको हम फिर से थोड़ा खोल लेते हैं। ओके, दिस विल बी अराउंड Sn of n. We can take k equal to 1 आउटसाइड, क्योंकि सिंपल सी बात है, यहाँ पर अगर आप log 1 रखोगे तो log 1 is 0, and that will give you a division by 0 problem. So इसलिए हम 2 को अलग से बाहर निकाल लेते हैं, 1 by 2, and our summation will change what? Our summation will change from k equal to 2, and this remains still the same, right? ये फिर भी सेम ही रहेगा, n divided by log of n, right? Okay, so let's write 1 divided by k ln of k. ओके, इसमें हमारा थोड़ा मैथ्स हल्का सा बढ़ेगा, पर जिसको नहीं पता है कोई बात नहीं है। इफ यू हैव रेड अबाउट इंटीग्रेशन, अगर आपको इंटीग्रेशन के बारे में थोड़ी भी नॉलेज होगी, सो जो इंटीग्रेशन का बेसिक आइडिया है वो समेशन पे आता है। ओके, व्हेन यू सम अप इन्फिनिट नंबर ऑफ थिंग्स, यू बेसिकली गेट एन इंटीग्रल, राइट? सो आई कैन से अगर मैं 1 by 2 को थोड़ी देर के लिए हटा दूं, लेट्स रिमूव दिस फ्रॉम पिक्चर, क्योंकि सिंपल सी बात है, इसको बाद में हम ऐड ही कर देंगे। सो लेट्स से कि Sn मेरा बराबर है दिस होल समेशन, राइट? k equal to 2 up till n divided by ln of n, 1 divided by k ln k. So I can say कि if I convert this problem into an integral problem, तो सिंपल सी बात है, इंटीग्रल प्रॉब्लम में क्या होता है, आप इनफाइनाइट समेशंस लेते हो, राइट? आप इनफाइनाइट समेशन लेते हो, ठीक है? और जिसको नहीं पता है, आप समझ लो कि वी कैन बेसिकली कन्वर्ट दिस प्रॉब्लम इनटू फॉर्म ऑफ इंटीग्रेशन, एंड ये लैंड अप करेगा कुछ इस तरीके से, दिस विल बी लेस देन और इक्वल टू द इंटीग्रेशन फ्रॉम 2 अप टू n डिवाइड बाय log ऑफ n, और ये चेंज हो जाएगा dk डिवाइड बाय k ln k से, राइट? बी विद मी, बेयर विद मी, ओके, जस्ट लुक एट द मैथ्स, घबराओ मत, इट इज वेरी इजी, ठीक है। ये चीज याद रख लो, बस आपको इतना चीज पता होनी चाहिए कि दिस समेशन विल गेट कन्वर्टेड टू दिस इंटीग्रेशन, और हमने लेस देन इक्वल टू साइन लगाया है, व्हाई, बिकॉज दिस विल प्रोबेबली बी लेस देन, क्योंकि इसमें इंटीग्रल में इनफाइनाइट समेशन होता है, और समेशन में हम डिस्क्रीट टर्म्स को सम अप करते हैं, दैट्स व्हाई वी कैन से कि इसकी वैल्यू हमेशा ज्यादा बड़ी ही आएगी, राइट। सो इवन इफ वी गेट एन अपर बाउंड, वी कैन क्लोजली से कि ठीक है, कोई प्रॉब्लम नहीं है, राइट। सो नाउ व्हाट आई राइट, आई विल राइट वाई एस एन इज लेस देन इक्वल टू द इंटीग्रेशन। अब इसका इंटीग्रेशन क्या होता है, व्हाट इज द इंटीग्रेशन ऑफ दिस थिंग, ये क्या है, ये डी के एल एन के क्या होता है। नाउ जिसको भी थोड़ी बेसिक मैथ्स पता है, अगर नहीं पता है नॉट अ प्रॉब्लम, द इंटीग्रेशन ऑफ 1 डिवाइड बाय के एल एन के वुड बी इक्वल टू व्हाट, इट विल बी एल एन ऑफ के, ठीक है। इसका जो इंटीग्रेशन आएगा 1 डिवाइड बाय के एल एन के का, दिस विल बी एल इंटू एल एन ऑफ के। अगर आपको डिफरेंशिएट करके देखो, इट विल बी 1 अपॉन एल एन के, फिर उसके बाद एल एन के का डिफरेंशिएशन 1 बाय के आता है, तो इट विल अगेन लैंड अप देयर, राइट। तो दैट्स व्हाई इसका जो इंटीग्रेशन आता है वो एल एन ऑफ के आता है। सो वी राइट दिस एज 2 एंड दिस विल बी एन ऑफ एल एन बाय एन, जो कि इसका अपर बाउंड है। अब हम इसमें लिमिट्स पुट कर देते हैं खटाक से, लिमिट्स पुट करेंगे, सो दिस विल बी व्हाट, दिस विल बी एल एन ऑफ एन डिवाइड बाय एल एन ऑफ एन, राइट। हाँ, ओके, डिवाइड बाय एल एन ऑफ एन। इसको थोड़ा सा नॉर्मल फॉर्म में लिखता हूँ, कंफ्यूज ना हो जाओ आप, एन डिवाइड बाय एल एन ऑफ एन, राइट, एंड माइनस एल एन ऑफ टू, ठीक है। ये बेसिकली हमारा समेशन बन के आता है, राइट। अब इसको जरा ओपन कर देते हैं, इसको जरा ओपन करेंगे तो दिस विल बिकम व्हाट, दिस विल बिकम एल एन ऑफ एल एन एन माइनस एल एन ऑफ एन, ठीक है, माइनस एल एन टू, ओके। अब आप देख सकते हो कि दिस एल एन वैल्यू, अब आप यहाँ पर लॉग एन है, और यहाँ पर क्या है, लॉग ऑफ लॉग एन है, सो दिस विल बी एक्चुअली मच बिगर देन दिस थिंग, राइट। दिस विल बी मच बिगर देन दिस थिंग, इससे बहुत बड़ी होगी, दैट्स व्हाई वी कैन एक्चुअली इग्नोर दिस टर्म। इन अ सिमिलर वे हमारा एन अगर बड़ा होगा, वी कैन ऑल्सो इग्नोर दिस टर्म, क्योंकि ये भी बहुत छोटा है, राइट, ये भी काफी छोटा है। सो व्हाट आर वी लेफ्ट विद, वी आर लेफ्ट विद एल एन ऑफ एन, जो कि क्या है, लॉग ऑफ एन। अच्छा, अब वापस ऊपर आते हैं, हमने एस एन क्या बताया था, हमने एस एन बनाया था इसको, दिस वॉज आर एस एन, राइट, ये हमारा एस एन था, इसका मल्टीप्लीकेशन किसके साथ होना है, एन के साथ में। सो व्हाट इज द टाइम कॉम्प्लेक्सिटी, आवर फाइनल टाइम कॉम्प्लेक्सिटी इज व्हाट, इज टी ऑफ एन इक्वल टू एन इनटू log of n, and that is how you prove the time complexity of sieve of Eratosthenes। मैंने यहाँ पर प्रूफ कर दिया है कि ये इसकी टाइम कॉम्प्लेक्सिटी कैसे आती है। इट इज अ बिट कॉम्प्लेक्स, अगर आपके ऊपर से गए नॉट अ प्रॉब्लम, इट इज एक्चुअली नॉट रिक्वायर्ड, बट जस्ट फॉर एनीवन हु इज क्यूरियस अबाउट दिस, कि इसको जानना है कि आखिर कैसे काम करता है, एंड इफ यू गो फॉर एडवांस मैथमेटिक्स आपको नहीं समझ में आएगा, दैट्स व्हाई फॉर यू पीपल आई हैव ब्रॉट डाउन अ वेरी सिंपलर वे, जिससे आप समझ पाओ कि अच्छा ये काम क्यों कर रहा है, कैसे कर रहा है, इसका टाइम कॉम्प्लेक्सिटी क्यों ऐसा आ रहा है, इतना कॉम्प्लेक्स क्यों आ रहा है। सो आई हैव टेकन डाउन अ बेटर सिंपलर प्रूफ, बट यू आर फ्री टू चेक आउट द एडवांस प्रूफ, आप उसको चेकआउट कर सकते हो, बट फॉर टाइम बीइंग हमने ये चीज प्रूव कर दिया, एंड दैट इज हाउ बेसिकली यू प्रूव द टाइम कॉम्प्लेक्सिटी ऑफ सी। अब इसके कुछ एडवांटेजेस डिसएडवांटेजेस होते हैं, वो बात की बात है, बट आई थिंक वी हैव कवर्ड अ लॉट इन दिस वीडियो, क्योंकि ये टॉपिक बड़ा था, दैट्स व्हाई आई वांटेड टू मेक अ सिंगल वीडियो ऑन दिस कॉन्सेप्ट। सो आई होप दैट you are able to understand कि how sieve of Eratosthenes work, और क्यों ये इतना एफिशिएंट है, हाउ डू वी गेट द प्राइम वैल्यूज, और फिर हमने इसका कोड भी लिख के देखा, इसकी टाइम और स्पेस कॉम्प्लेक्सिटी भी डिस्कस कर ली, राइट, एंड वी आल्सो डिड अ प्रूफ वर्क। सो आई थिंक कि इट इज नॉट डन इन अ लॉट ऑफ लेक्चर्स। आई थिंक कि आपको बहुत जगह पे ये पढ़ने को नहीं मिलेगा कि इसकी टाइम कॉम्प्लेक्सिटी कैसे आती है, that's why I have brought this for you. So if you like the explanation, if you like the concept, if you like the approach, then do like, share, subscribe and comment करो, अगर समझ में आया तो कमेंट में कमेंट करो अंडरस्टूड, और लाइक मार के जाओ, सब्सक्राइब करो, everyone who is new to channel subscribe, and please hit the bell icon so that you never miss an update from my side. And till then, we'll meet again tomorrow with another problem, with another not problem, with another topic in continuation with our number theory series। हम इसी में आगे और भी कॉन्सेप्ट्स पढ़ेंगे, अभी बहुत कुछ बाकी है नंबर थ्योरी में जो कि रिक्वायर्ड होता है, and we'll cover something else at the part 3 of this of arrays and mathematics। Until then, bye bye guys, good day ahead।